Now let's talk about the Bohr model of the hydrogen atom spectrum. We'll start by talking about the spectrum that you would get for just white light. So if you use a white light source like sunlight or an incandescent light bulb, and you pass the light through a prism, you can separate the light by wavelength into all of its constituent colors. And you get a continuous spectrum. You see every single color of the rainbow. Now, if in contrast you use a different type of light bulb, like a fluorescent light bulb or like a hydrogen lamp, what you do is you'd fill the hydrogen lamp with hydrogen gas, and then you would pass an electric current through it. There would be an electric discharge that would ignite the lamp, and the light that's given off from that could be passed through a prism. And when you separate the light based on its wavelength, what you end up seeing is, instead of a continuous spectrum with every single wavelength of light and every color of the rainbow represented, you only get discrete lines in the spectrum corresponding to light that only has specific wavelengths. So you'll see light with a wavelength of 410 nanometers and is violet in color. You'll see light that's 434 nanometers and is blue in color, and you don't see anything in between. The same can be said for the spacings between all of these other lines in the spectrum as well. So why is it that you don't see a continuous spectrum? Why are all these other wavelengths missing here? This is a phenomenon that really was confusing for a lot of scientists, and they couldn't come up with a good explanation for why this was the case until Niels Bohr came up with this model for the hydrogen atom. In Niels Bohr's model for the hydrogen atom, what he said is that you have your proton at the center, and then you have the electron orbiting around the proton, but this electron can only occupy discrete energy levels that are fixed. These are the only places the electron can be. So the electron can be sitting on level 2, or it could be sitting on level 1, but it cannot be sitting anywhere in between. It can't be at like 1.6. It has to be at one of these discrete orbits. Now, for the electron to move between energy levels, let's say that it was on level 2 and it wants to go up to level 3. To go up to a higher energy level, the electron has to gain energy. It's going to absorb energy by absorbing light. And if the electron wanted to go down to a lower energy level, then it would have to emit energy in the form of light. And that's how you're going to be able to get an emission spectrum. This is one way that we could represent the model for the hydrogen atom, but it's also helpful to take a look at a diagram that shows the energies of these levels. Now, it's important to keep in mind that the proton and the electron are attracted to one another. And because of that, the lowest energy will be energy level 1, when they're as close to one another as possible. To move the electron further away from the nucleus to level 2, you have to add energy to pull apart these dissimilar charges. So when we see the energy diagram, we'll see energy level 1 is the lowest on the energy scale here. And then as we climb the energy scale, we get to level 2, level 3, level 4, and so on. Now, as I mentioned previously, for the electron to change energy levels, you have to absorb or emit light. So once again, I'll say that if your electron is here on level 2, and you wanted to move up to a higher energy level, you would have to absorb light. And likewise, if it were on level 2 and you wanted to go down to level 1, light would have to be emitted so that the electron is releasing energy to fall to a lower level. Importantly, the energy of the photon that is absorbed or emitted will be equal to the difference in energy between the two levels, right? So the energy of light that's absorbed in this case will be equal to the energy of this level minus the energy of that level. That difference in energies will be the energy of light that gets absorbed. Now, because you have discrete energy levels like this, you're going to only get certain energies of light that can be absorbed or emitted. Like, for instance, you can go from energy level 3 to energy level 1, and you would emit light with a certain wavelength. You can go from energy level 2 to level 1, and you would emit light with a different wavelength, but you're not going to see anything in between because it's impossible for the electron to start at n equals 2.6. The electron can only occupy these fixed orbits, and so you're only going to get very specific changes in energy between levels, and you're only going to get very specific energies and wavelengths of light that can be absorbed and emitted. Think of this energy scale as being kind of like a ladder, right? Think of every step on this as being like a rung on the ladder. The electron can be standing here or here, but it cannot be in between. If you tried to stand in between two rungs of a ladder, you would fall off, and it would be bad news for you, right? The same sort of thing applies for the electrons. It can either be here or it can be here, nowhere in between. And because of that, you're only going to get fixed differences in energy, right? You can go from 3 to 1, you can go from 2 to 1, but you can't go from 2.6 to 1. And so that's why you're not able to see any other wavelengths between those two. Let's take a look at a conceptual problem here. In this question, you're asked to determine for which of the following transitions will the wavelength of emitted light be the shortest. Is it the n equals 3 to n equals 2, n equals 4 to n equals 2, n equals 2 to n equals 3, or n equals 2 to n equals 4? Take a moment to think about this and put in your answer. All right, I added the energy diagram to kind of visualize what's going on here. And first thing that we can do is recognize that in this problem, we're dealing with emission of light. And so right off the bat, we can eliminate a couple of answer choices. Notice that in choices C and D, you're going to higher energy levels. And so in those two cases, light would be getting absorbed. And so those two would be eliminated, right? Because again, in this case, light is absorbed, and the same in this case. And in this problem, we're dealing with the emission. Now we have to figure out whether A or B is the correct answer. And so to do that, we're going to take a look at our energy diagram here and draw the two transitions. So for one of the transitions, we're going from n equals 3 to n equals 2. And in the other, we're going from n equals 4 to n equals 2. The energy of the light that's being emitted will be equal to the difference between the two energy levels. Now, how do we relate that to the wavelength of light? Remember that energy of a photon is inversely proportional to wavelength. So if you want a short wavelength, right, a small lambda, then that means that you need a big energy. And therefore, we need to find the case where you have the biggest difference between the two energy levels, and that's going to be the n equals 4 to n equals 2 transition. You have the biggest delta E, and so that means that it's going to be the largest energy of the photon emitted, and that means it's going to have the shortest wavelength. And there we have it. In our next video, we'll take a look at a calculation-based problem.